Hello, everyone. This is Guohui Wang from Alibaba Group. Today, I'm going to talk about the SONiC telemetry in the wild. We'll share our development and deployment experience of the SONiC telemetry feature in our production network. Okay, in the last couple years, we have a very large-scale SONiC deployment in our data center network. Our data center network is similar to a lot of others with the three tier of the switches in the cloud topology. This picture shows the architecture of our DC network. We have three tier switches we call ASW, PSW, and DSW. All the stereo switches are using single chip switches and in the multi-plane expansion architecture. Our SONiC switches are deployed on all the Alibaba design switches in all the tiers. In the last couple years, we have deployed SONiC switches in full DC data centers across 5 regions. SONiC has become a key infrastructure component that supports our all core businesses such as search, ads, e-commerce, cloud, and financial services, etc. And those pictures shows some of our own Alibaba design switches running all the different DC tiers. Building on top of the SONiC, we use SONiC as an open platform, which allow us to redesign our network management operation. It bring in an evolutionary change to our network operations. We have built a rich set of features for the network configuration management, telemetry, deployment, and how we upgrade the network. There are several of the key features. One, we move the network telemetry and management from traditional command line interface into a gRPC-based system. We using Docker-based software management and upgrade. We use OpenBMC for hardware and environment management. We also build customized protocols and tools for our operation efficiency. Also, open network operating system. We build a SONiC emulator, which support full device virtualization to achieve faster iteration and also the offline network verification. Today, we'll have a deep dive into the network telemetry part. So, what is network telemetry? Network telemetry means different things to different people, right? There are a lot of keywords you can see of the telemetry, visibility, metrics, monitoring, data collection, etc., etc. For us, network telemetry is about monitoring of network states. It's about visibility into what is happening in the network. It's also about the data collection and data collection and analytics for the management and the operation purposes. Back in 2018, we have built a SONiC telemetry module, which support the gRPC dial-in and dial-out mode that can collect the data from the system SONiC system DB, and also we later extended to support non-DB client as well, and all this data can be streamed out from SONiC into telemetry data collector. So the SONiC telemetry module features high performance gRPC channel. It also supports the real-time streaming telemetry features with structured key value data format. We have also shared the SONiC telemetry module into community. Internally, building on top of the SONiC telemetry module, we have developed a rich set of network telemetry applications to improve the visibility of both control plane and data plane of the network devices. So those applications allow us to provide a lot more information about our software, hardware, and the traffic statistics, and also flow level information into the network. For example, we support event-based real-time monitoring for software and hardware failures. We're also using the OpenBMC log analysis to monitor the hardware and environment changes. Also, we also have the link optic analyzer. We support the high precision counter for the traffic stats. On the data plane side, we have in-band telemetry, high performance telemetry engine, etc. Due to the time limit, today the talk will be focused on the event-based real-time monitoring, high precision flex counter, and also a data plane high performance telemetry engine and its smart flow application. So first, let's look at the event-based real-time monitoring. The event-based real-time monitoring is designed to have a real-time monitoring of the software and hardware failures happening in the network. So instead of rely on traditional SMP pooling to collect exceptions or failures, we want to have a built-in monitoring infrastructure on the SONiC itself to monitor the error, failure, or exceptions in the software and the hardware running on the SONiC switches. And those failures will be managed in the event format and stream out into our network monitoring system at real time. This has been a very important infrastructure to provide high reliability and allow us to handle the failure quickly in the network. The design of the event-based real-time monitoring looks like something like this. We build the syslog analyzer and the process watchdog to monitoring the exceptions in the SONiC applications. And also, to monitor the process states of those applications. This will be saved into an event DB in a SONiC DB system DB. And we have a process manager and the event analyzer to process those events on the event DB and generate notifications. And those notifications will be right into notification DB. And those notifications will be sent out to the stream processing system in our backend to generate alert to the network operators, so that people can be notified about all those failures in the system and handle them quickly. We support a lot of different metrics and events to monitoring the software and hardware and system status. For example, in the software monitoring, we have a protocol status, state consistency, syslog exceptions, and process status, etc. We can monitor the hardware, the power, the fan temperature, memory errors, and also the optical module in the hardware side. On the SDK, we support a parity error and error counter and SDK exceptions. On the system side, we support the Docker exception, memory and disk usage and CPU usage, those kind of events in the real-time monitoring system. Here we shows two of the event monitoring in our production network. This is actually the final alarm that was sent into our DINTalk application. You can see those are the failures related to the SFP error or the NDP protocol status. One experience we have been seeing in the production deployment of those kind of monitoring system is that when there are a lot of the devices deployed in the network, the volume of those real-time monitoring events could be very large, and if the raw data could be very noisy because there are always something going on in the network. So the data filtering and post-processing is important to make those events and alert useful for the network operators. So we have built the filtering and analytics infrastructure on the backend to filter some of those event noises and correlate them to generate the correct alarm for the network operator to look into. So the data filtering and the correlation is very important for the production monitoring. And in our production network, we have seen all those kind of kernel panic, Docker panic, and memory leak, and CPU failure, etc. Those kind of failure events in the network. Okay, the second item is about the high precision counter collection. The motivation of high precision counter is from this. Let me give you an example of a 5-second microburst on a 24-bit port. So on a traditional SNP based counter collection channel, so we're using SNP pooling with a 1 minute interval, because that's what the SNP based system can support. So those coarse grain counter collection has a problem to detect those kind of short term microbursts. For example, a 5-second microburst will be shown as a long range of low volume traffic on a SNP based counter collection system. So the information is too coarse grained. There's not much details to show this microburst. The high precision counter we want to achieve is to try to achieve the second granularity high precision counters. So given, for example, given a 1 second high precision counter, we can observe those short-term microbursts. This 5-second microburst can be shown clearly on the monitoring system, give us a lot of information about the traffic volumes and status stats. However, implement the high precision counter collection on SONiC has a couple of challenges on both the collection side and also the channels, the gRPC channel side. We using 1 second collection granularity, and we implement the counter grouping mechanisms on the SONiC to batch the data so that we can reduce the SDK pool into the ASIC, the counter SDK pool into the ASIC. We also optimize the DMA channel allocation to improve the rate performance for high frequency counter collection. Also at a high frequency counter collection, the timer drifting could become a bigger problem, because a little drift in the timer could cause a big accuracy drop in the counter collection and calculations. So we're using a single timer on the local on each switch, and the local timestamps. We also have a bunch of the timer drifting optimizations to improve the accuracy of the counter collection. Of course, on the gRPC side, we implement the connection retry, message queuing, channel heartbeat, and also gRPC server failover mechanisms to improve the reliability of the counter collection, so that those systems can be used reliably in our production network. This picture shows a microburst congestion observed in our production network. Actually, this happened during the 11 event. So from this picture, you can see that there is a very short period of time in the network with actually low traffic rate. But from the 10 meg Q watermark metric, we can see that for a short period of time, the Q number 1 is overflowed for a very short period of time. Those kind of detailed information can only be observed with high precision counter collection implemented in SONiC system. It actually allows us to look into the details of the congestions and help us to explain some of the short-term packet loss and improve the network troubleshooting capabilities. Okay, let's look into the high-performance data plane telemetry engine. For a lot of the telemetry use case, we would like to collect data from the chips and switch ASICs about the data plane activities, right? So today, there's only one path between the switch ASIC to the CPU, which is basically the control path on today's SONiC. The control message from the switch ASIC will go through a bunch of the control queue, and it will go through the SDK kernel module and the network stack on the host, and through the socket library API and to the control applications. We found a couple problems of using those kind of channel for the data plane telemetry application. One is the data plane telemetry application usually have a lot more data volume between the switch ASIC and the CPU. Those data, the telemetry data, when they are mixed with the control message, it could actually hurt the performance of the control applications. The second is the normal control path application, control path channel on today's SONiC has a performance issue because all the control packet has to go through the host kernel. So to provide the high performance data plane telemetry channel, we separate the control message and the telemetry data, and we implement a high performance data channel using a user space library that bypassed all the kernel. So those data plane telemetry data will be put into different CPU queues, and those data will bypass the host kernel and send directly into the data telemetry applications running on top of the SDK UNet libraries. And those applications can implement the pluggable application modules that can implement flexible logics for the data analysis. Okay, Smart Flow Analyzer is one application we have implemented on top of the data plane telemetry engine. The idea is on the switch ASICs, we can implement something like a mirror on drop table that can mirror all the packet dropped on the pipeline and MMU with drop reasons and send them through the data telemetry, the data telemetry engine, and send to a detailed applications running on the SONiC. So the telemetry application on the SONiC can perform proactive drop flow and monitoring analysis and maintain a detailed drop reason for each of the flows. And those applications also provide configurable interface for packet collection and alert. Those can provide a rich data set for the network troubleshooting to monitoring the drop, the packet drop activities. Okay, to summarize, we have a large-scale SONiC deployment. We also have a large set of the network telemetry applications developed on SONiC. We found the high-performance, low-latency telemetry application is very critical to the network operations. In the large-scale telemetry application deployment, the data filtering and the post-processing is very important for the real-time production usage of the telemetry features. Also, a lot of data plane telemetry features require stronger ASIC support and better compatibility between different chip vendors. For the call to action, I would like to call for the community to work together to build a stronger telemetry support with a high performance, low latency, and a flexible data format and a processing interface for the full post-processing of the data sets. I will also call for the compatibility between the different chip vendors in terms of supporting the in-band telemetry or the data plane telemetry features. That's all. Thank you, everyone. Okay. Just give me a second. I think there's some kind of reflection on the phone. Okay, let me try to answer some of the questions on the. This is like, by the way, this is Guo Hui from Alibaba. Let me try to answer some of the questions on the chat. Okay. Select, the question is SDK UNet library part of the community image? Is there Git link to the lib? No, actually. Okay, let me put it this way.
We use the UNet we use the UNet library as an example of actually how we implement the high performance data channel on SONiC. But I think this for this kind of stuff we have to work with particular vendor SDK. It's actually tied to the particular vendor SDK. For people actually for like the SONiC community kind of version, people probably have to work with different vendors for those kind of different data channels. We also have some kind of debate between if we should just using direct SDK UNet library, or we should just using the Ethernet port, or using some kind of DPTK kind of libraries for the user space kernel bypass. Yeah, I mean this is just actually just to summarize, the answer is actually no. This is the SDK UNet library is not part of the community image. We put it here just to show as an example of how to provide high performance data channel on SONiC. The second question from Benjamin is, which of those pieces will be contributed into the SONiC community? Yes. We would love to actually contribute some. Well, for those telemetry applications, there are some telemetry applications are very much tied to our management system, but there are some actually the part are really common. For example, our optimization on the high precision counter and gRPC channel reliability improvement, we definitely would like to work with the community and in the future to contribute into the community. But I think we also would love to work with the community to on those high performance data channel part. But for a lot of the application specific logic, for example, the data the real-time monitoring, the data filter logic or the code, this is very much our management specific. So I think this is hard to contribute. But generally, yes. In general, we will definitely like to work with the community and contribute those common infrastructure part into the SONiC community. Another question from Anissa is, would you be able to share the SDK and ASIC this has been implemented? We generally don't talk about the vendor specific in those kind of setups. But definitely we are open to work with the mainstream ASICs on this one, and the example we put in there is actually really depends on what ASIC you use, right? So let me see. Oh, but by the way, for the SDK and ASIC kind of question, a lot of the data channel and user space data channel between SDK and the user space is actually all available in most of the switch ASIC vendors. See that one more question. Event monitoring read from EventDB is via SDK kernel module class? No. For the real-time event monitoring, all the data is actually all this data rate is all from the user space. So for whatever event we put into the EventDB, this is already processed data basically. This is already either in the syslog we filter and extract it from the syslog, or is from the process state we're running on the system. By the time we get the data, it's already in the user space, and all this data will be right into EventDB, and we have the analyzer basically read the event and do another round of filter. This is actually all has nothing to do with the control path. Basically, this is all user space, all above, even actually above the system DB at that time. Okay. Oh wow, there's a lot of more questions in the QA section. A question from Arcadia. Okay, what is your opinion on using counters versus real-time event to detect microburst? Counters are still not real-time, even they are higher precision. Yes, counters not real-time. I think for the microburst, we have to, for the microburst, we don't really have a good way to detect through real-time event as is today. We have to basically rely on the counters or the traffic stack to detect the microburst. So on today's, a lot of the ASICs actually, well, some ASICs may support, but some not. On today's ASICs, a lot of ASICs don't support, for example, the microburst detection from the ASIC side. So if in the future there are more ASICs supporting the real-time event or the real-time exceptions from the ASICs to support the microburst detection, I think it will be something useful. We can definitely incorporate into the real-time event monitoring on the upper layer applications. I hope that answers the question, Katia. You meaning ASIC needs stronger data plan telemetry for any specific that you have in mind. In general, so okay, there are several parts of this actually. A lot of different ASICs have a different that have the compatibility issues in terms of data plan telemetry. For example, a lot of the metadata and also the headers are not compatible between different chip vendors in the INT or the inbound telemetry space. This is one thing. The other thing is actually, for example, we would like to know more about the latency and drop, exception, error, or like the microburst you mentioned, right? Those kind of events directly from the ASIC. But I think today there is I do see solutions coming up from different chip vendors as a different for different part of it. But I don't see a like comprehensive solution that really support those kind of focus on the support of those kind of telemetry features from ASICs. But I think if I think this is probably the timing is actually people are really realize the problem in this space, and they are actually proposing different solutions from different chip vendors, which is actually a good thing. I would love to see more comprehensive solutions, and also a standardized efforts across different chips in the community in this space. Another question from Silak. One more question. Event monitoring. Okay, this is actually already answered, I guess. Okay, Acadia. Yes, understood. Sounds like video decision making sure that uniform capability across ASIC. Yeah, uniform capability across ASIC is definitely one important aspect. I will add another aspect of this is actually the flexibility to the users or to the not developers in terms of how to process the data on the top. So I don't think we can rely everything on the ASIC to realize all those kind of telemetry features. It would be nice to have the flexibility of the data processing capability from the ASICs, so that the developers in the NOS side can actually have more filtering or data processing powers. I think this, like I mentioned in the talk, we realize that actually data filtering and correlation is really important to make the data useful in the production. Okay, I guess I answered all the questions. I'll wait for another 1 or 2 minutes, so that if the audience has more questions, they can please post in the QA or the chat window. Thanks, Shane. So I guess that's it, right? So we are 1:30. All right, thank you, everyone. Thanks for joining the talk.